Welcome to this deep dive. So, usually when we look at adversarial attacks in machine learning, there's this expectation of, like, highly specialized rigid engineering.
Oh, absolutely. It's historically been very localized.
Right. I mean, for you listening, as an expert navigating the bleeding edge of machine learning, gradient-based optimization inside and out, to fool an image classifier, we're so used to calculating the gradient of a loss with respect to the input pixels.
Yeah, you take that step in the direction that maximizes the error, right?
Exactly. Generating noise perfectly calibrated to, well, one specific model and one specific objective.
But then you step into the world of modern, massive, multimodal architectures, and that rigid optimization pipeline just completely fractures.
It really does.
We're looking at a landscape where adversarial generation is moving from a localized math problem to something much more universal. I mean, foundation models aren't just isolated classifiers anymore.
No, they're complex agents, right? Parsing visual inputs, segmenting scenes, executing intricate logic.
Exactly, which is why our focus today is so critical.
Yeah, today we are deconstructing a newly published arXiv paper that basically flips that entire methodology on its head.
It's a fascinating read.
It is. The paper is DarkLLM, Learning Language-Driven Adversarial Attacks with Large Language Models, by Yifeng and researchers from Fudan University, Nanyang Technological University, and Tongji University.
And their mission here is huge. They've essentially trained a large language model to translate natural language instructions directly into pixel-level adversarial noise.
Which is wild. They've completely replaced the traditional, one target, one optimization paradigm with a single 1 billion parameter framework.
Right, a framework that unifies targeted, untargeted, segmentation, and multimodal attacks all under one roof.
So before we get into how they did that, we should probably look at the limitations of current methodologies that necessitated this in the first place.
Yeah, that makes sense. Because over the past decade, the field has relied heavily on white box techniques, like the fast gradient sign method or projected gradient descent.
Or, if you don't have white box access, you default to black box transfer generation using surrogate models.
Right. You optimize the perturbation on a surrogate you actually control and just sort of hope the adversarial features transfer to the target model.
And that works beautifully if your goal is incredibly narrow.
Exactly. But if you want an untargeted attack against a vision transformer and then say you want to attack the segment anything model or SAM,
you're building two entirely different attack pipelines from scratch.
From the ground up. Existing untargeted methods are strictly tailored to specific architectures.
And targeted attacks, where you're steering the output to an adversary-specified target, those require a total pipeline redesign for every new objective.
Yeah, the computational overhead of re-optimizing for every new target or architecture is just, it's completely unscalable.
It's like forging a highly specific custom key for a single lock. If you want to open a different door, or even open it in a different way, you have to melt the metal down and start over.
That's a perfect analogy. And the authors recognize that the dynamic integration of recognition and reasoning modules in modern systems demands something better.
Right, an attack framework that is actually transferable and scalable across heterogeneous models without re-optimizing from scratch every time.
Which led them directly to this embedding as attack paradigm.
So to abandon task-specific pipelines, we need a universal controller. And they chose an LLM for this.
Specifically, they went with InternVL 2.51b.
Right, the 1 billion parameter version, and they fine-tuned it using low-rank adaptation, or Lorala.
Exactly. But an LLM generates text, right? To make it a visual adversarial controller, they had to modify the vocabulary.
Okay, so they introduced special control tokens for different attack types.
Yeah, like they added specific tokens for targeted vision language attacks versus segmentation attacks.
I'm trying to trace the flow here. So the model receives the user's instruction, it parses the semantics, and then if an attack is required, it embeds one of these special control tokens into its text response.
Yes, but the text response is just the surface level. The real innovation happens underneath in the latent space.
Okay.
They extract the final layer hidden state that corresponds specifically to that inserted control token.
Because that hidden state holds the LLM's rich, latent semantic understanding of the requested attack, right?
Exactly. It represents the concept of the attack mathematically. That state is then projected through a two-layer, multi-layer perceptron to form a refined, high-level attack signal.
Okay, wait. I need to push back on this modality gap for a second.
Sure, go ahead.
I understand extracting a latent representation of intent. The vector holds the semantic concept of, make the model fail to segment this image.
Right.
But how does a high-level semantic concept actually cross over to become mathematically precise pixel noise? I mean, a vector of semantic meaning is fundamentally different from a grid of image perturbations.
That is the core question. And that translation requires a dedicated module, which they call the conditional perturbation generator.
Okay, so what is that exactly?
It's essentially a decoder network designed to refine random noise embeddings that are sampled from a standard normal distribution.
Okay.
And to ensure the random noise actually takes on the adversarial properties requested by the LLM, they employ a cross-attention mechanism.
Right, so the random noise embeddings act as the query in the attention mechanism.
Yes. Exactly.
While that latent attack embedding we extracted from the LLM serves as both the key and the value.
You've got it. So the noise is effectively asking the semantic attack vector how it should shape itself.
Wow, that conceptualization is brilliant.
It really is. The noise attends to the attack instruction, basically injecting the specific adversarial intent into the spatial domain.
Right, so the math there computes the softmax of the noise query multiplied by the attack key and uses that distribution to weight the attack value.
Precisely. And to refine this even further, the generator architecture includes self-attention layers to capture global spatial dependencies across the noise itself.
Which is then followed by transposed convolutions for the spatial upsampling, right? Translating latent features back into high-resolution spatial features.
Exactly. And finally, bilinear interpolation resizes the generated perturbation so it matches the target image's specific dimensions.
But to guarantee this is actually an adversarial attack, the noise has to remain imperceptible. It must be bounded mathematically.
Right. Otherwise, it's just corrupting the image in obvious ways, which defeats the purpose.
So how do they enforce that?
They apply a ton activation function at the very end of the generator. This strictly bounds the final visual perturbation to a predefined norm constraint.
So depending on whether they're attacking a multimodal LLM or a segmentation model, they apply different bounds.
Exactly. Like an L infinity norm of 16 over 255 for targeted MLLM attacks or 10 over 255 for SAM attacks.
Ensuring the noise stays within a mathematically defined envelope of imperceptibility while still carrying the semantic payload.
Right. The constraint guarantees the noise remains subtle enough to bypass human detection.
Okay, generating semantic noise is an elegant structural solution for the local generator, but translating that to a completely unseen black box model is a different universe.
It's the ultimate test, really.
Yeah, because if the noise isn't transfer, it's just a lab curiosity.
Yeah.
How does this survive transfer without falling apart?
Transferability is the core challenge their optimization strategy had to solve. For vision language models, DarkLLM uses this massive surrogate scaling strategy.
Okay, what does that look like in practice?
Well, during distributed training, they don't just optimize against a single surrogate. They utilize an ensemble of 16 distinct CLIP models.
16. Wow, okay.
Yeah, mapping different architectures and pre-training datasets across different computational nodes to compute the gradients jointly.
So it forces the generation of highly generalized adversarial features.
Exactly. By forcing the generator to find a perturbation that satisfies all 16 CLIP variants simultaneously, it prevents the noise from overfitting.
Right, it stops it from just memorizing the idiosyncratic features of any single architecture. But the segment anything model, Sam, is fundamentally different from CLIP. It's heavily prompt dependent. You can't just throw 16 CLIPs at it and expect fine-grained segmentation to fail.
You're right. Attacking SAM poses two distinct hurdles: prompt transferability and backbone transferability.
So how do they handle the prompts?
To solve the prompt issue, they use a multi-prompt ensemble strategy during optimization. For any given image, they randomly sample a diverse set of point prompts and box prompts.
Okay, so optimizing a single perturbation to suppress predicted masks across all those sample prompts encourages a sort of robust prompt-agnostic segment-nothing behavior.
Exactly. The model learns a perturbation that breaks the segmentation logic regardless of how the user actually queries the image.
Got it. But if I remember correctly, the backbone transferability for SAM is where they hit a wall with standard loss function.
They absolutely did.
Because if you use standard mean squared error to match the predicted mask to a target, wouldn't the perturbation just overfit to the exact activation magnitudes of the surrogate SAM model?
You've identified the exact bottleneck the authors discovered regarding cross-backbone transfer.
Right.
I mean, squared error penalizes the exact magnitude difference between the predicted and target masks. So when you optimize an attack using it, you learn how to precisely manipulate the specific numerical outputs of that exact neural network layer.
The adversarial noise becomes perfectly tuned to the specific activation scales of the surrogate model,
Yes.
which means the moment you apply that noise to a different architecture, say, one with a higher parameter count or different layer normalization, the attack falls flat.
It completely fails. But switching the objective to a binary cross-entropy loss solves this.
Really, just swapping the loss function.
Yeah, because binary cross-entropy doesn't care about matching exact regression magnitudes. It simply pushes mask predictions toward the all-background decision boundary.
Oh, wow. So by optimizing for the decision boundary rather than the activation magnitude, the gradients become semantically aligned.
Exactly. You are targeting the fundamental concept of the background rather than the numerical quirks of the surrogate model.
That is a massive shift in optimization logic. Here's where it gets really interesting. Sometimes the bottleneck isn't the architecture, but the fundamental assumptions of the loss function, forcing the model to over-index on the wrong signals.
And it vastly improved transferability to unseen backbones like Sam Huge. The geometry of the decision boundary is just far more stable across model scales than raw activation magnitudes.
But wait, combining all of this unifying untargeted attacks, highly specific targeted language attacks, and segmentation attacks into a single LLM framework.
It's a lot to balance.
It is. If you just throw those diverse loss functions and gradients into a joint training loop, the optimization is going to tear itself apart.
You're completely right. You have fundamentally different objectives competing for the same parameters.
Right. Unifying these heterogeneous attack types has to lead to severe convergence imbalance.
It does. The authors noted a critical failure in their early joint training experiments. Untargeted attacks, which basically just need to push an embedding away from its original class, converge incredibly fast.
Right. It's easy to break something.
Exactly. Targeted attacks, on the other hand, require deep language-sensitive understanding to pull the embedding toward a very specific semantic space.
It's much easier to just shatter a plate than it is to carefully sculpt it into a bowl.
Yeah, and the untargeted attacks would generate these massive parameter updates that dominate the optimization.
Completely overriding the model's ability to perform targeted attacks.
Yes. So, to prevent the easy tasks from overriding the complex ones, they developed decoupled progressive training.
Okay, so they decouple them? How does that work?
They separate the generators based on their control tokens to ensure no gradient interference across incompatible objectives. So training happens in two distinct stages.
Got it. What's stage one?
Stage one is targeted instruction tuning. They fine-tune the LLM controller and the targeted generator on massive image datasets, specifically ImageNet and Conceptual Captions 3M, using QA-style data.
Focusing entirely on mastering semantic parsing and executing complex targeted commands.
Right. They learn the hard stuff first.
It's like teaching a chef to master a highly delicate, complex souffle first. Once they've perfected it, you freeze that skill in their brain.
I love that analogy.
And then you throw them into a chaotic, fast-paced diner kitchen to learn short-order cooking. If you tried to teach both at the same time, the souffle would be ruined every time.
That maps perfectly to stage two, which is unified attack training. They initialize the LLM with those stage one weights, but completely freeze the targeted generator.
You lock in the complex skill.
Exactly. Then they train the untargeted and multimodal generators.
So the LLM learns to route to these new, faster converging objectives without its internal representations of the delicate targeted attacks being washed out by the aggressive gradient.
That's it, exactly.
So the architectural design, the boundary-focused loss discovery, the decoupled training, it all builds to the experimental validation.
And the evaluation covers 4 tasks and 13 datasets across 15 different models.
Let's look at the hard numbers. How did it perform?
The targeted attack results on frontier multimodal LLMs are particularly striking. Using an open-source 2 billion parameter controller setting, DarkLLM achieves a 67.7% attack success rate on GPT-4o.
Wait, 67.7% on GPT-4?
Yes, and over 60% on Gemini 3 Flash. It consistently outperforms previous state-of-the-art universal baselines like any attack.
That is insane. Over 60% of the time, a universal visual perturbation generated by a comparatively tiny open-source model forces GPT-4o to output an adversary-specified response.
It completely shatters the assumption that massive parameter counts inherently protect foundation models from generalized adversarial noise.
It really does. And what about for segmentation tasks?
DarkLLM causes massive drops in the mean intersection over union metric across SAM-based, SAM-huge, HQ-SAM, and even the newer SAM2 architectures.
Wow.
It consistently induces that segment-nothing behavior regardless of user prompts, outperforming existing universal adversarial baselines.
That's incredibly consistent.
Furthermore, the generated semantic features proved highly robust against standard preprocessing defenses like contrast and brightness adjustments.
Transformations that typically shatter standard gradient-based noise.
Exactly.
As robust as it is, we need to analyze the physical boundaries of this method. The authors impartially reported specific failure cases, right?
They did. For example, the perturbation struggles on images with highly complex backgrounds.
Mechanically, why does high-frequency background detail neutralize the attack?
The hypothesis is that high-frequency details inherent in a complex image effectively mask the adversarial noise.
Oh, okay.
The target model's convolutions process so much natural variance that the subtle, bounded adversarial perturbations are just diluted.
So the signal-to-noise ratio works against the attack, scrambling the local gradients that the adversarial perturbation relies on to cross the decision boundary.
Exactly. There's also a fascinating failure case regarding monochromatic objects like a flat orange or a plain car, specifically when a user applies a box prompt.
Okay, so if I draw a box around a plain orange, the attack fails to induce segment nothing. Why is that?
When a user provides a box prompt around a simple monochromatic texture, it provides an overwhelming spatial prior to the segmentation model.
Oh, I see.
The combination of that strict bounding box and the lack of internal texture variation makes the model highly resilient. The bounded adversarial noise simply cannot overcome the strong spatial prior provided by the user's prompt.
So the model relies entirely on the box boundary, effectively ignoring the subtle semantic noise introduced by the attacker.
Right. These limitations beautifully highlight the physical boundaries of the imperceptibility constraint rather than a failure of the language-driven paradigm itself.
Absolutely. So, to pull this all together, DarkLLM fundamentally proves that by reformulating adversarial generation as an instruction-conditioned synthesis problem, a single LLM can act as a master orchestrator.
Yes. By utilizing latent attack embeddings and cross-attention, it generates highly transferable, pixel-level attacks across completely heterogeneous vision models.
Completely bypassing that localized optimization trap that has bottlenecked research for a decade.
And as foundation models scale and integrate into multimodal agent pipelines, understanding these unified semantic vulnerabilities is no longer just a robustness exercise.
It's an urgent security imperative.
Absolutely. The attack surface has fundamentally evolved from isolated math to universal language. A single language instruction can now synthesize noise that transfers across discriminative classifiers, generative models, and fine-grained segmentation systems simultaneously.
It exposes a systemic structural vulnerability that we have severely underestimated, which leaves us with a critical question for you, the listener, to
A
consider.
very unsettling one.
If a single, universal visual perturbation generated by an LLM can simultaneously compromise both the coarse-grained semantic alignment of a model like CLIP and the fine-grained boundary detection of SAM2.
What does that tell us about the foundational architecture of these supposedly distinct models?
Exactly. Are they truly learning different features or just wearing different functional masks over the exact same structural vulnerabilities? Something to think about.